A satellite has been reported to fall out of the sky over this rectangular region of houses. So there must be houses inside of there, right there. So it's in this rectangular region. Billy has a circular swimming pool in his backyard with a radius of 15 feet. So that would be this, and it's got a radius of 15. So I'm going to put that information in my picture. What is the probability that the satellite lands in Billy's pool? And I didn't grab a highlighter there, sorry, but probability is what they were wanting us to find. Probability is a very simple thing to find. The way I define probability is what you want to have happen divided by the total possibilities. So I will abbreviate it as want over total anymore, but it's what you want to have happen divided by total possibilities. So what's the probability that the satellite lands in Billy's pool? So the satellite is going to land in an area. We totally need to find the area of these shapes. So we're going to go off to the side, and we've got the area of the circle. So area of the circle will be pi r squared, and the area of that circle, the radius is 15, so 15 squared, we should know that, is 225. And I'm going to keep it exact, 225 pi. I'm not going to approximate until we're all done. So always keep everything exact until we're ready to totally give our final answer. And the area of where the satellite is definitely going to land in, that shape is a rectangle because they told us so. Even though it doesn't have the 4 right angles, they say it's a rectangle. So area equals length times width, and that's going to be the area of the rect. And that's going to be 60 times 150. So 60 times 150 is 9,000. So we know that that satellite is guaranteed to land inside the rectangle somewhere, and it just so happens that that pool is inside the rectangle. So it's quite possible that that satellite could hit the pool, but they say geometrically, that's what this is geometric probability. We want it to land in the pool, so that is 225 pi for an area. That's how much space that takes up out of a total of 9,000. So there's our exact answer right there. We could reduce that down and do the 225 over 9,000, but I'm not so concerned about that. I want to do more of an approximate answer. So we're going to do 225 pi, and notice this, I'm going to put the 225 pi in parentheses because that numerator has like more than one term. So, and I want to divide that by 9,000. And I'm going to change this to a percent, to the nearest tenth of a percent. So remember, to change your percent, you got to move the decimal 2 places over, and that's about 7 point, it's either going to be 7.8 or 7.9. Since this is a 5, this has to be rounded up, so about a 7.9% chance of that happening right there. So we did geometric probability. We wanted it to land in the pool. This is the area of the pool. Total area of 9,000. So on 11 here, we've got ourselves a target. The target has 3 basic circles here. So what I'll do is I'll grab ye old highlighter, and we'll call this outside guy, he's basically like a big blue circle. And then inside of that, I've got this orange circle. And then inside of that, let's go with this green circle. So there's like 3 circles there in that situation. They say first off, what is the area of each circle? So let's roll with it. I'll do the area. I'm not going to call it the blue circle because I don't have it highlighted, but we'll call it the area of the outside. So area of the out is pi r squared. Remember, we got to start with the formula. And its radius is 25, right, because they tell us so. So area of the outside circle equals 25 squared. So if you don't know that, we can always punch that in. That would be 625 pi, and that would be inches squared. But we're going to keep that exact because that's all I really care about in this situation. Then we've got to do the area of that orange circle, which I'll have to do in red because I don't have an orange color here. So the area, I'm going to call that the middle So the area of the middle is pi r squared, and that area of the middle is 14 squared times pi, so that would be 196 pi, and that would be in inches squared. And finally, the area of that green guy, which is the, let's just call it the area of the small, is pi r squared, and that would be 64 pi. So each little circle, you got the green guy, he's got 64 pi inches squared, and the red guy, aka the orange guy, and the outside guy. Well, what is the area of the shaded region? Well, to find the area of the shaded region, it's pretty cool.
So you can see here that the target is made up of 3 different circles. You've got this giant outside circle right here, and then the inner circle, I could call it the middle circle actually, and then you've got the small inside circle right here. Well, they want us to find the area of the shaded region, which in this picture is pink in that situation. So to find the area of the shaded region, this guy doesn't matter one bit. So we can throw away the entire outside circle. It doesn't matter. But see, it's not just the area of the middle guy. We got to take away this situation here to where what we're actually looking at is we've got that same middle circle, and we have to subtract away the inside circle to where we have nothing left here but the ring.
So we see that we got to take the area of the middle guy and take away the area of the inside guy. So I'm going to do 196 pi, take away 64 pi, and see these are like terms because they both have a pi with it. It's like 196x minus 64x. So all I have to do is totally just take those coefficients minus each other and realize that that's 132 pi. That's the area of the shaded. So let's kind of label that area of the shade equals 132, SH for shade, and that'd be inches squared. Well, they say, what is the probability that the dart will land in the shaded region if the dart is thrown at random? So they're back to probability again. And remember, probability is what we want to have happen divided by the total in that situation. So they want it to land in the shaded region, which we know the area of the shaded region is 132 pi. The total of that guy is going to be the entire blue circle, because that blue target right here, if you turn that around, this is how big it is. It's the entire thing right there. So that blue circle, we found his area also. That thing is 625 pi. And cool thing about keeping it exact is when you've got the same thing upstairs and downstairs in a fraction, like you got a pi over pi, it totally cancels each other out. So we got 132 divided by 625. We don't even need the pi's. So that is about, let's just keep that like exact since it came out so nice. This is nice and clean. So it's a 21, sorry, I want an equal sign, 21.12% chance, because we moved that decimal 2 places to the right, and since that's nice and clean, I didn't even round it off. So that's the probability that a dart that's like guaranteed to hit that. Now we all know that if you throw a dart, you might even miss the target altogether. So we're going to take an example, or take for granted is what I'm trying to say, that it's going to hit the actual circle itself, but the chances if it was just at random that you threw it and it landed in the shaded region is 21.12%. Cool. More probability. Give the probability that the spinner will land in region A. So we can see here, this is region A. Thank you, letter A. And remember probability, I like to do the W over T, what you want over total. We want to land in region A. Well, you notice they're giving me all these degrees of this circular spinner right here. Well, we want to land in region A, and that's 40 degrees. Out of the total target, you could add all of these up together, but I hope you know that in a circle there is 360 degrees total, and this is actually pretty simple to reduce because I can cancel them zeros right here, and you get 4 over 36, which is 2 over 18, which is 1 over 9 if you want to reduce that, and then we could divide that out. 1 divided by 9 is 0.1 repeating, so that's about 11.1% chance in that situation. So because you move that 2 places to the right and then round into the nearest tenth. So want over total. So Dave is running in this pattern below. So Dave's going to run from point A to point D. Good for Dave. If Dave trips at random, what is the probability that he will trip between points B and C? So boom, boom, between points B and C is right here. They want probability, so I'm going to do want over total. We want to know if Dave trips in region C. Well, that's 1250 feet divided by the total distance. So I got to add those together. So 2000 plus 1250 plus 2200. The total target is 5450. And we will punch that in. 1250 divided by 5450. And that is about a 22.9% chance that he trips randomly in that spot right there. And just one more of these bad boys, baby. Find the probability that a point chosen at random is in the shaded region. So you can see the outside shape is totally a circle, totally a rectangle, and we've got circles inside of this. And here's what we need. We need to find the probability. So we got to do want over total, and we want to land in the shaded region. Well, the area of the shaded region is a goofy shape, right? So we have to figure out what that is. And wouldn't that be the rectangle, the whole big thing, take away these two circles? So I need the area of the rectangle. That's going to be length times width, and the area of the rectangle is going to be 12. I'll let you skip those steps when they're that simple. You know, it's 4 times 3 is 12. The area of the rectangle is that. But to find the area of the circle, what we want to notice is, like, I need the radius. So area of the circle is pi r squared, or I need a diameter so I could find the radius, you know, but they don't give me that. But what they do give me is this information right here. This whole distance is 4. So to find the area of these circles, I need a radius or a diameter. Now, the problem with this guy is they don't tell us that these two circles are congruent. We have to assume it. Sure, they look the same, but they don't tell us. But see, this distance right here is 4. This is definitely true that this distance right here is 4. And assuming that these two circles are the same, they're congruent to each other, that means that this guy is 2 and this guy is 2 for diameters of this bad boy. Meaning the radius of each circle is 1 in that situation. So the area of the circle is going to be, like, let's just call it this circle. This blue circle right here is 1 squared, so it's just going to be pi. And like I said, if these circles are congruent, then this circle over here is going to be the same thing. So I have 2 of those guys. So the area of the shade is going to be the big guy, which is the rectangle, which is 12. Take away the 2 circles, so together they have an area of 2 pi. So I'm going to go ahead and punch that in, 12 minus 2 pi. Oops. 2 pi, and I'm going to keep that number in my calculator, but when I write this, I'm going to say that it's 12 minus 2 pi, that's the exact area, over the total area, which was 12, and the pen is not working very well, I apologize for that. So here's that number, 12 minus 2 pi, I should have not rounded it off, I'm just going to divide that by 12, and totally get about a 46.6% chance that point chosen random is in the shaded region situation. So the area of the shade is 12 minus 2 pi, and we figured that out. We didn't round it because we don't want to round until we're done. Divided by 12. So cool, man. That's our lesson 2.5 on area, perimeter, circumference, geometric probability. Let us know if you have any questions, and have a good one.